Okay, this is the third lecture on stacks. Some announcements first that you presumably know about. In today's video, we're going to talk about yet another application of stacks, how to convert an infix expression into a postfix expression. So here are some infix expressions, a plus b down there, a plus b times c. And we want to look at these in hopes that we can get some insight into the process of converting an infix expression into a postfix expression. So a plus b, if you remember, we've got, there's only one operation here. The operands are going to come before the operator. Pretty straightforward in that case. Here we've got, but as we're going through this, I should say, we come across, when we think about automatically translating this infix into postfix, and assuming we're scanning the string or the expression left to right, when we hit that plus, we're going to have to set it aside and remember it. So after we hit the B and write the B down, the second operand, we'll know what operator to write there, and then we'll hit the end of string here. In this particular case, same thing, we're scanning left to right. We hit an operand. We'll write that operand down. We'll come to the plus. We're going to need to remember that plus, not so it can immediately follow the B, because after the B, we've got an operator of higher precedence than that addition operator. So we're going to write the B when we encounter it. We're going to check this operator. It's not the end of file or end of string as it was in this case. We're going to look at this operator. We're going to ask, is this operator of higher precedence than the operator we've already encountered here? And the answer is yes. So we're going to write that one of higher precedence down first. And then finally, we're going to write the addition operator down. So even in these very simple examples, you can see some principles that we're going to have to follow. When we hit an operand, we simply write it to output or wherever we're going. When we hit an operator, we remember it at least as long as it takes to look at the next operator to see if it's higher precedence. And if it's the same precedence because of the left to right convention, we would want to write this operator down first before this operator. Before writing even this higher precedence operator down, though, we've got to write down the second of its operands. So that's why you see all the operands there. And then you see the multiplication, which we have also set aside and remembered. So after we wrote the C down, we would know to write that. And then we write the addition down. So here are some other examples of infix expressions that you're going to have to, that we're going to translate. Again, with this idea of getting understanding into the process of translating. If you want to take a moment, pause the video and see if you can solve any or all of these problems before we reveal the answer. So pause now if you want to. Okay, so here are some answers to those, the answers to these infix expressions. In this case, we scan left to right. Again, we're going to remember operators as we go. We're going to write down operands as we encounter them. Here, we've remembered this addition operator so that after we write this down at a minimum, or whatever we need to write here, we can remember that and recall it and output it, which we've done right there. In this case, though, we haven't got a multiplication which is of higher precedence. We've got something of equal precedence. And because it follows to the right of this, that addition is actually going to take precedence over the subtraction operator. So we're going to be writing A, B. We encounter the subtraction. It's of equal precedence, ordering aside. So we write down the addition operator, which we set aside. And then we write down the second operand for that subtraction. Then we write down the subtraction. Yet another example. Here, we're going to be scanning left to right, writing down operands as we encounter them, remembering operators as we go. This multiplication is of higher precedence, and so we're going to write down its second operand and then write it down. The only reason we wouldn't write it down is if we came across something of greater precedence here, which we're going to do in the next example. But we write that multiplication down. And then we write down the addition, because the next operator in the string is a subtraction, which is of equal precedence as the addition. The addition comes to the left, so we write it down. Now we write down the second operand for the subtraction and then write the subtraction operator. In this case, we've got a delimited sub-expression, and we're going to be scanning through this. A gets sent to output, addition gets remembered, B gets sent to output, multiplication has a higher precedence than the addition which we've set aside. So we're going to now translate what follows that multiplication operator. That's going to be written before that. In this case, though, we don't write down the multiplication operator immediately as we did up here, because we've got something of yet higher precedence than even multiplication. And so we're going to translate this C minus D next. And that's where we get this. We scan to the left, right. That open paren tells us we're about to scan over a sub-expression. And when we hit that closing paren, we know we're done with that sub-expression. And what we've translated between those two parens, we've written down in the process of translating that sub-expression. And then we're done there. After we hit that, we still got two items on the stack. Those items are operations. And I've actually jumped ahead. When I talk about setting aside and remembering that addition and remembering that multiplication so that we can write them down later, guess what? We're going to use a stack to implement that memory. And it works out perfectly. We write down the multiplication, which is going to be at the top of the stack at the time we hit the end of string. And then we write down the addition, which is going to be the other operator on the stack. And in fact, that addition is going to be the very last operation that we want to execute in this infix, and it's the very last operation in the corresponding postfix. Yet another example. Again, set aside this, put it onto a stack, set aside this because what we've got coming up has higher precedence. Basically translate what is in that sub-expression, which is going to be this part of the string, and then empty out the stack with the two operators that are on top of the stack. The addition, again, is going to be the very last operation. This is very much like this, except I have something of equal precedence to that addition rather than greater precedence to that addition. And so scanning, scan in A, output it, remember the addition for after minimally the next operand. In this case, we hit an operator, we output the B. We hit an operator of equal precedence to the addition, so we print out the addition. And then we translate this sub-expression just the way we did before. And we've got this final subtraction operator, which corresponds to this one that is on the stack and still has to be printed out. Again, these are more complicated expressions. We're pretty much ready to move to an algorithm, but I do want to give you a chance to translate these as an exercise. So pause the video and translate as many of these as you want to or can, and then restart the video and we'll talk about the answers a bit. So these are the corresponding answers. I'm not going to go through all of these. This is to some extent, some of these are interesting because they begin with sub-expressions. Here we would translate the sub-expression into this right here. We hit the multiplication operator here. We print out the operand first, and then we print out the multiplication operator. Here we've got some nested parens. You know, every time the insight we're sort of gaining here is when we hit a left paren, we want to remember that we're starting a sub-expression. How are we going to remember that we started a sub-expression? We're going to push that left paren on top of the stack. And then we're going to be processing the rest of the expression after that open paren until we get to a corresponding closed paren. And this is where this problem of balanced delimiters that we talked about in the very first stack video is important here, because I'm going to hit a second open paren here, and I'm going to push that on top of the stack too. And I'm going to process this. I'm going to hit a closed paren. When I hit that closed paren, I will have translated that expression, that sub-expression, sub-expression into a postfix form. I'll hit the 3 and then the subtraction, because this is part of yet another sub-expression. Hit the end of sub-expression there, output the 2, output the multiplication. So this is interesting because it's got nested parens. And there's some other interesting problems here that you might want to try. We would translate this sub-expression, which would be translated right here. We would translate this sub-expression. The effect of going through our translation process would translate this sub-expression here. And then when we were all done with this second sub-expression, that division operator would have been remembered and printed out last. So if we take, you know, just some general guidelines that we've, perhaps insights that we have from going through these many examples, this is a strategy that we might use to implement an algorithm for doing the translation. If we encounter an operand, we just output it. If we encounter a sub-expression that starts with an open paren and ends with a closed paren, we're going to end up translating it through the very process that we're currently sketching. If we encounter an operator, then if there are any other operators of higher or equal precedence that we've encountered before, then we want to output those higher, earlier operators that we've encountered before. And as it turns out, again, we have saved on a stack. We want to print those out before printing out the operator we've just encountered. So it's time to move to help organize these thoughts a bit. And here we have an algorithm for algorithm sketch in C++ pseudocode for, or very general algorithmic pseudocode for how we're going to process this. We're going to be scanning the infix expression from left to right. Each time we scan a character, if it's an operand, we're going to output it. If it is a open paren, then we're going to push this onto a stack, and remember that we're just starting a sub-expression. If what we just scanned in is a closed paren, then we're going to look to the stack to get the items that are important for translating that, in particular, everything we're putting onto the stack in this application are operators or parens. And so what we're going to have here are we're going to be outputting operators on the stack, which is going to turn out to be in an inappropriate order until we get to a corresponding open paren, which is on the stack. And at that point, we're going to stop. Otherwise, if the character we've just read is a operator, if the stack is empty, already empty, we're going to push that operator to remember it minimally so that we get past the next operand, we can output it. If the stack is not empty, we're going to want to remove operators that are on the stack, have been set aside and remembered, that are of greater than or equal precedence to the operator we've just encountered. And when we've done that, when we've outputted those earlier operators of equal or greater precedence, then we're going to push the operator we've just encountered. And we're going to repeat these processes. And then in a few examples, we saw that we're going to end up outputting the anything that remains on the stack. Those are going to be the final operators that appear in the postfix expression. So before moving on, TOS, by the way, in this algorithm stands for top of stack. Before moving on, here's an example we're going to be looking at. Why don't you see if you can translate this, not just arbitrarily, but see if you can take time and actually use this example to work through this algorithm. So translate this using the particular algorithmic sketch that we've got here. And when you think you've got it, then restart the video. So again, hopefully you just didn't translate to postfix, but you actually use this to walk through the algorithm. Let's take a walk through the algorithm. We've got a minus x plus c times d. So the first character we're going to scan in is the a on the far left. The stack is empty in this case, in this example. And we're going to simply output a because a is an operand. We now scan in the subtraction operator. What are we going to do with that? We're going to push it onto the stack. A is still the only thing in the output. We encounter the open paren. We're going to push that onto the stack. We're entering a sub-expression. And so we've got two items on the stack now. A is the only output. We encounter X, that's an operand. So stack remains the same. We simply print out that X. The addition operator, we have an operator. We're going to push this because there are no prior operators that are on top of the stack. We have a left paren on top of the stack, but that is not an operator of equal or greater precedence. It is part of a sub-expression that we're still in the midst of translating. AX is still the output. We get the C, that's an operand, stack remains the same. Output the C, so remember that. We're now scanning in the multiplication operator. Push that on top of the stack because the addition operator, which was on top of the stack, is not of greater than or equal precedence to that multiplication operator. So the multiplication operator is something we want to do first before the addition operator. So addition operator stays in the stack, multiplication operator goes onto the stack. So we remember it after we've processed its operands. Output is the same. Encounter D. Stack remains the same. Print out D. Now we hit the close paren that closes our sub-expression. We're going to process, having hit that closed paren, we are going to start outputting the operators that are queued there. I shouldn't say queued, but are currently on top of the stack, and we're going to be getting those top of stack operators, the multiplication followed by the addition, until we get to the open paren that delimits where the sub-expression ends. Sorry, my queue is, or my cursor is not working again, so hopefully you followed that. But we process the multiplication, print it out. We process the addition, we print it out. We hit the matching paren, and so we stop. There's just one thing on the stack now. And now we've hit the end of the string or file that contained the infix expression. We pop out anything that remains and print it out. Okay? So that is more or less what that algorithm is doing, that algorithm sketch. Here's a bit more formality to the pseudocode for the process we've just talked about. It's represented a little more cleanly as case statements, but we've made the stack declaration explicit. We have got a variable called postfix that we've initialized to the empty string there at the top. And we have 4 cases. If the character we've just read in is an operand, if it's a left paren, if it's a right paren, or if it's an operator. And then after that for loop of processing characters, we're going to empty out the stack. So we're just going to quickly take a look at these 4 cases in order. Again, this is pretty straightforward. In this case, outputting the operand corresponds to simply appending it to the end of this postfix string that we're building up. If we encounter a left paren, we're simply going to push it to indicate where our sub-expression started. If we encounter a closed paren, we're going to keep looking at top values, and so long as we don't find the matching open paren at the very start, we're going to append whatever is on top, which is going to be an operator, at the back of the postfix expression, then pop off that operator. And we're all done looping through there, popping off operators that have been set aside. We're going to pop off that the matching open paren that we find for the closed paren there. And finally, if the character is an operator, we're going to go through and so long as the stack is not empty and the stack is not a open paren, indicating that we're in the midst of translating a sub-expression, we are going to process characters which have greater than or equal precedence to the top. And we're going to put those top characters of operators of equal or greater precedence than the operator we've just encountered at the end of the postfix expression, and then we're going to pop them off. And then we're going to push the operator we just encountered on top of the stack. And at the very end, we simply empty out the stack in the way that we've illustrated before. And we return the postfix expression that we built up. Just a couple things to mention before we finish up. This precedence function that we've referenced informally, could be written like something like this. That is, addition and subtraction have a precedence of 0. Multiplication and division should have a precedence greater than that, so we make it 1. Otherwise, we return some value, or we throw an exception, or do something to indicate that it's not part of this family of operators that we are assuming here. Should say that, this could work for this general procedure as long as we updated the alphabet of operators and the precedence function to reflect other kinds of operators. We could use this for instances where we had infix expressions of other binary operators besides addition, subtraction, multiplication, division. And in some arithmetic languages, those would exist, and we could still use it to convert to postfix. And they might have different levels of precedence beyond simply the 2 that we've talked about here. Finally, in addition to postfix expression, you remember from the last lecture, we also have prefix notation. And prefix, and you should know how to, you should go through some exercises, but in prefix, we put the operators before their corresponding operands. And so here we've got a multiplication operator that's going to be applied to the next 2 operands. Here we've got an addition operator that's going to be applied to this operand and whatever this evaluates to. And then we've got a subtraction operator that is going to be applied to whatever this evaluates to. and this final operand D. And so same situation down here. This is one sub-expression. This is the translation of the other sub-expression, and we're going to multiply those together. So in prefix, the very first operator that applies is the last operator that we would actually apply. So that's it for the stack lectures. Next, we'll talk about cubes.